What's going on, everybody? It's Mr. Gus, and I'm back in the physics conference room. Today, we're going to talk about the ideal gas law. So we've been talking about thermodynamics. We talked about heat exchange, specific heat, thermal conductivity. But today, we're going to talk about a sample of chemical, gas sample, that does hold the heat or exchange the heat or use the heat. And we're going to examine that a little more closely. So we have a way of describing a gas, and it's known as the ideal gas law. The ideal gas law is a mathematical expression that describes a sample of gas. And we actually have two, because we can actually describe a sample of gas in two different ways. The first way we can describe that sample of gas is we can describe the entire sample. If we look at the entire sample of gas, we can explain this using one of the ideal gas laws. The entire sample, we would use the equation P times V equals little n r capital T. Now these are some variables we haven't necessarily seen before. I'll move you a little bit closer. This here is pressure. This here is volume. This here, N, is number of moles, a little blast from the past in chemistry. We have to know, if we're talking about the whole sample of gas, I want to know how many total particles, all the particles in this sample. So I need to know number of moles in that case. Over here, this is an ideal gas constant. We'll call it the ideal gas constant, the IGC. And then over here, this is temperature measured in Kelvin. Okay, so I've got pressure. Pressure's in ATM. Volume is in liters, and I know this because I have whatever my constant is in my unit for the IGC is in Kelvin. It's in liters. It's in atmospheres, and it's in number of moles. So this is, if I'm going to look at the entire sample of gas, I want to use PV equals nRT, number of moles, and then the ideal gas constant R, which is atmospheres, liters, and Kelvin. The other way I can examine this is I can examine this in terms of like a single itty bitty particle, or at least in terms of number of particles, right? Number of moles is counting how many groups of particles there are. But perhaps I want to just examine all the particles all at once and the particulate level as opposed to more of a macroscopic level. If that's the case, I can use the equation written like this. PV equals N, capital N, right? K, B, capital T. This equation is essentially the same, except I have two different things. I've got pressure, boom. I've got volume, boom. I've got capital N. Capital N is actually number of particles, not number of moles. So I'm taking my number of moles and I'm multiplying it by Avogadro's number, which is 6.022 times 10 to the 24, something like that. You go ahead there, okay? KB is known as the Boltzmann constant. Boltz, I think it's got two N's. The Boltzmann constant. The Boltzmann constant is unique because it's unique to number of particles, not number of moles. That's the only reason to have different constants there. And then lastly, temperature is also in Kelvin. So they're basically the exact same thing. It's just looking at this sample of gas from two different perspectives. Either the whole system in terms of number of moles, or on the macroscopic, the super micro, sub-microscopic scale of number of particles. And all it does is change big N, little n, R, and the Boltzmann constant. We'll talk more about that later, but this is the ideal gas law, okay? What we should know about the ideal gas law is that actually the ideal gas law tells me if there's any work being done, and as it changes, if there's a change in this gas constant, right? It tells me pressure times volume, the ideal gas law, will tell me if the gas is doing work on something based on if it changes. Let me show you how that works. We know that pressure is a measurement of, pressure is force over area, which is newtons per meters squared, right? I'm sorry, meter area is meters, pressure is, meters cubed, squared, times volume. Volume is meters cubed. And when I look at this, I end up with newtons times meters, which is also equal to a joule, which is just energy. Basically, that's all it is, right? So if I think about what pressure is, and pressure times volume ends up telling me how much work a gas sample can do based on its change in pressure and volume. So we're going to look at three processes now. That's the ideal gas law in a nutshell. We're going to look at 3 processes here that gases can do and see how they relate to the ideal gas law. So I'm going to have to go ahead and erase this here. Understand that pressure, volume, those are, we need to get rid of all this stuff actually now, because now we should know this. Get rid of all this, and we'll kind of reframe this a little bit in terms of the processes I want us to be able to look at. All right, the first process we're going to have is going to be called isometric. Let's go with isometric first. Isometric. Iso means same, metric means volume. So let's go ahead and think about what an isometric process looks like. Let's put the ideal gas law down here. PV equals nRT. I'm going to use the moles version just because of my degrees in chemistry, and that's just kind of like the one I think of when I think of it. And let's go ahead and track our pressure and volume. So if something is isometric, that means that there are changes taking place where our volume is going to stay the same. If the volume stays the same and other things change like pressure or temperature, right? If volume stays the same and let's say I increase the temperature, if I increase the temperature here, what's going to happen to the pressure of this sample of a closed system? We'll say that the number of moles does not change. But if I increase the temperature, what is going to happen to the pressure in order to keep this thing isometric? I'm going to also need to see an increase in pressure. So let's say I have volume here. We'll say that's point A. And at point A, the temperature is increased somehow. If the temperature is increased somehow, I'll move myself up here. That would be an isometric process because the volume stays the same. But if this is going to happen, it's going to require an increase in temperature. And then when I see an increase in temperature, I'm going to see an increase in pressure. And that should make sense, right? If I increase the temperature of a sample of gas, and the volume doesn't change, those particles will bounce off each other faster. And so you'll see an increase in pressure. This is known as isometric. The next example we have would be an isobaric sample. Right? Isobaric means same pressure. So let's hold pressure constant. If I'm going to hold pressure constant, let's see what happens if I increase the temperature now. If I increase the temperature now, but the pressure stays the same, in order for my pressure to stay the same under an increasing temperature, I will have to increase the volume. So I would see my pressure staying right here, or my pressure starting here at point A. Temperature increases. If pressure is going to stay the same, I know that my volume will have to increase, and so my PV graph looks like this. And so I see this as the process that takes place here from point A to point B. Now, before we go on to the third process, I have to ask you a question. Is there work being done on this? Is there work being done on either of these systems? I'll answer it in a later video, but for now, we just discussed what P times V is. You consider as we're going through this, is there any work done by the gas, on the gas? What part of the graph could I use? Because these two graphs are different. One is vertical process, one looks like a horizontal process. Ask yourself, I wonder if there's work being done. We'll answer this in the next video we do on processes and on the first law of thermodynamics. All right, last one. Sorry, this was, I didn't write it. They didn't write it isobaric. Isobaric. Same baric, same pressure, same barometer, same pressure. Last one. The last one is, what about isothermal? So I've done same pressure. I've done same volume. What about same temperature? Not same heat, same temperature. If I hold temperature constant, right, P and V. Let's say I start here. If I hold temperature constant and I expand the gas, I take that piston and I pull that piston out, I'm creating more space. But if temperature stays the same and the particles don't move around faster, if I increase the piston, like I grab this, I lift it up, I increase the volume. If I increase the volume, let's start over here. Let's say I increase the volume. Let's say we're here, and that's called A. If I increase the volume, if I increase the volume but don't change the temperature, increasing volume, what has to happen to pressure in order to keep temperature the same? Well, it has to go down. And it doesn't go down in a line because pressure is inversely related to volume. So it can't be linear. Instead, even though it looks linear, we need to have this inverse shape taking place here. So I'd be going from A to B, from A to B, from A to B in all three processes. But this here is known as isothermic because it is the same temperature. Okay? Again, we're basically just taking an equation, our math skill, and applying it to these graphs, our graphing skill, okay? So that's the ideal gas law. These are the three basic processes. We actually have 4 processes, but these are the 3 most common processes that we will come across. We'll do the 4th one a little bit later, okay? For now, this is all we got. If you got questions, you drop in the comments, you send me an email, you ask me in class, all right? Till next time, see ya.